Okay, so we'll go ahead and get started. Are there any questions before we begin? So today and Monday, we'll use these two lectures to talk about carbohydrates. So carbohydrates, they're polyfunctional molecules, but really they have oxidation state 1, alcohols, and then oxidation state 2, aldehydes or ketones. So they sort of fall in between modules 2 and 3. So we'll introduce them now. And Monday, you have your second exam. Again, that will be through zip grade. So we're going to talk about carbohydrates, which are biomolecules. Most of you are biology majors, so at some point, you might take biochemistry or molecular biology, and so carbohydrates are important structurally in those classes as well. So we'll give an introduction to the bonding patterns and what are the typical sort of classes of carbohydrates. They're commonly called sugars. So everyone's familiar with sugar. I have a sugar-free Red Bull. I switched to sugar-free about 2 years ago after drinking like straight Red Bull for about 20 years and figured out that I just couldn't handle the amount of sugar that's like in a can of anything. On Monday, we'll do a little bit of taste testing of natural versus artificial sweeteners, and so you'll sort of get a chemosensory understanding of how structure impacts taste. And we'll talk about like how much sugar is in an actual can of soda. I'll show you how much, and you'll probably be amazed. So just as the word says, a carbohydrate is a hydrate of carbon, and you see that in the molecular formula. So they're basically just polyols, which means it's a carbon backbone with many alcohols. So plants fix carbon dioxide through photosynthesis. So that reaction is shown here. You have X moles of carbon dioxide in the atmosphere plus Y moles of water catalyzed by sunlight. That's going to give you a carbohydrate. So there's the formula. So basically, for every number of X carbons, if you take out the H's and the O's as water, you get a Y number of waters for X carbons. And then you get oxygen produced. So that's why it's good to have trees around. So they sort of scrub the CO2 and they produce oxygen that we breathe. So humans don't do photosynthesis. So the sun shining on you, it does other things, but it doesn't produce carbohydrates. And we get our sugars through what we eat. And when you go into other classes, you'll learn more about the topic of metabolism. So metabolism is just breaking down a molecule into other things to provide energy. So basically, sugars give you the power for your brain to move your human spacesuit as we sit on the third rock from the sun here. So for every carbohydrate plus X moles of oxygen, you're breathing out CO2, produces water, and then the energy that is used to move. So if you do take biochemistry, you'll talk a lot about the thermodynamics of how this happens and the energy required for metabolism. So, for example, I think if you know who Michael Phelps is, the Olympic swimmer, and you read about him, when he was active, his daily caloric intake was like a crazy amount of calories, like over 10,000 or something. So the normal diet for your average human is about 2,500, I think what it's based on. So an athlete is like X number of carbohydrates. And, if you look at his physique, he's very slim and built, right? So he's not getting fat from eating that food. It's basically going to produce the energy used to train and swim. So, in this class, we're primarily focused on structure, and then other classes, you'll see the implications of how these molecules behave. So sugars are also called saccharides. So there's all these common terms. If you have one sugar, it's called a monosaccharide. And the individual sugars themselves can be thought of as monomers that when linked together form polymers. And that's typically how your body will store sugars, as some sort of polymer that's then sort of degraded to form these monomers that are then metabolized to give you energy. So some terms here, the number of sugar residues in a polymer gives the classification. So 1 sugar is a monosaccharide, 2 is disaccharide, 3 is tri. You get this weird sort of in between. 4 to 10 is called oligosaccharide, and then after 10, it's called a polysaccharide. So once you get up there, the chains get pretty long. And again, that's just like a storage unit for these saccharides. In this class, we're really just going to focus on carbon chains of the saccharides that are 3 to 6 carbons long. And so we'll look at the classes and what names they have. So again, this is pretty much just an introduction to the structure, physical properties, and some basic reactions. So for each chain length, there can be constitutional isomers of where the alcohol oxidation state is versus the other main functional group, which is a carbonyl, as either an aldehyde or a ketone. So again, some more nomenclature for carbohydrates. Aldehyde-based carbohydrates are called aldoses, and ketone carbohydrates are called ketoses. So they both end with OSE, and then the first part tells you about the carbonyl group in the chain. Our first column here is the number of carbons in the chain, 3 through 6. And translating that number into a word, so 3 carbons is a triose. So for the aldoses, where you have an aldehyde in the chain, those are called aldoses. There's 2 of them because there's 1 stereoisomer along that carbon backbone. So if we remember how we figure out the number of stereoisomers total, you do the stereogenic centers, and then it's 2 to the n. So that's where this number of stereoisomers comes from. The aldoses are the most common ones, and the ketoses they still exist, but they're probably a little bit less common. You'll see them in biochemical metabolism, though. A tetrose, there can be 4 aldoses of the tetrose class, because now you have 2 stereocenters in the chain, so 2 to the 2, that gets you your 4. And then that math just increases. So we're going to look at the logic of the aldoses going from the 3 carbon chain to the 6 carbon chain, what the structures are, and why you have so many stereoisomers. The other thing that's important historically is assigning R and S to the stereocenters, but carbohydrates use this old-timey nomenclature. that big D, big L, and that refers to only one stereocenter in the chain, and we'll point that out. Again, this is historic nomenclature since carbohydrates have been studied. I don't think it's ever going to go away. But one thing I can tell you is that of the naturally occurring sugars, they all have the D configuration. And what I mean by naturally occurring are the ones that we use in our diet. So D and L, you can think of them as those are the stereoisomers, enantiomers. So carbohydrates have the D configuration. And associated with stereoisomers was this property of optical activity. And when you put the sugar into a polarimeter, you get this sign plus or minus. And the plus was called dextro-rotatory. And the minus was called levo-rotatory. Those are sometimes abbreviated with a small d and small l. So like a D and an L. So that nomenclature is different from this big D, big L. So just keep that in mind. The big D, big L refers to configuration. The small d, small l is optical rotation. So we'll start with the 3-carbon monosaccharide, and shown here are the aldose forms. So that means, ald means aldehyde. So the IUPAC name of this would be 2,3-dihydroxypropanal. It's commonly called glyceraldehyde. So again, because carbohydrates were one of the first organic molecules really studied in depth, everyone's sort of throwing their own nomenclature at it, and it's just stuck throughout the years. So if we look in the center here where I have stated Fisher projection, Fisher, we'll talk a little bit probably on Monday about Fisher and his contributions to this area, but the projection is just a learning tool that's going to help us figure out the stereochemical relationship of enantiomers and diastereomers. And so you can see under the Fisher projection, the structure to the left, carbon 1 is an aldehyde, carbon 2 is a secondary alcohol, and carbon 3 is a primary alcohol. So for the aldoses, the aldehyde is at the top of the chain, and you'll always have a primary alcohol at the bottom of the chain. Then what changes is the number of secondary alcohols internally of the chain. So if you notice on this one, see there's that big D by carbon number 2. So that's called D-glyceraldehyde. The plus, again, comes from the optical rotation. Now, if you look at the other structure, that's the mirror image. And so only carbon 2 is the stereocenter. So again, we have one stereocenter, so 2 stereoisomers, and these are mirror images. So notice that's the big L stereoisomer, and then the optical rotation is now negative. So historically, the D and L refer to the penultimate. penultimate is not the last carbon, it's the second to the last carbon in the chain. So if you have an n number of carbons, it's n minus 1. In the D and the L, refer to the stereochemistry only at that carbon. D is assigned when the hydroxyl OH group is on the right of the Fischer projection. L, which is maybe as a mnemonic, it's to the left. So what does the Fischer projection actually mean? We know that carbon 2 is sp3 hybridized, so it has 4 sigma bonds. But the way it's drawn, you see how you have the vertical bond, then you have the horizontal bond, and it's like a cross. And we know that if it's tetrahedral, they don't lie in the same plane. So the vertical bond, maybe I'll highlight that in blue here. If you look over to the left, it's showing that's the longest chain. So on the vertical axis is the longest chain. Then on the horizontal axis are your substituents. And then notice how they're represented here. They're projected out towards you, like they're trying to hug you. But again, even that is not sort of the best representation, because the vertical chain, those groups are then projected back, even though they're sort of drawn in the plane. So the Fischer projection as drawn in the center two structures, again, is just a tool for helping you figure out stereoisomers. But in reality, because those carbons have geometry to them, just keep in mind the spatial orientation. So the penultimate carbon, if the OH is to the right, it's D. If it's to the left, it's L. And so the naturally occurring sugars are D, and non-naturally occurring ones are L. So pretty much every organism on Earth metabolizes D sugars. And this sort of concept is known as homochirality. So if you were to have a diet that consisted of L sugars, you'd probably end up dying, because they're not going to get metabolized and you would get no energy from them. So it's interesting to think about, living organisms in general are chiral, and then there's this field called abiotic, sort of like how did things come into being? Why is there only one preference for these stereoisomers? So if we have time this semester, we'll talk a little bit more about that, and how on Earth, we've sort of evolved to metabolize these things. And it's interesting to think about, because it gets down to like sort of the Earth's magnetic field and how one sort of pathway evolved over the other. So that's a hot topic in research. So on this slide, we see the two aldotrioses. Again, carbon 1 is the aldehyde. And then we also see that now the ketose form, that should not say aldo in front of it. That should say ketotriose. So keto means it's the ketone form. Now the carbonyl is at position 2. And what you'll notice is this molecule does not have a stereocenter. So there's no D or L associated with this one. So the aldoses always have the aldehyde at carbon 1. At ketose, the carbonyl group is internal from carbon 2 up until the N-1, so the penultimate. carbon on the chain. So your body will, under metabolic processes, the difference between the aldoses and the ketoses are that they're just constitutional isomers. So in some metabolic processes, the aldoses are isomerized to the ketoses. So again, the Fisher projection is just a tool to help us identify the relationship of stereoisomers. When we get up into the tetroses, we're going to have another stereocenter, so 2 to the 2 is 4 stereoisomers. And at that point, it can get a little bit harder to determine what pair are enantiomers and then what are diastereomers. And then as we increase to 5 and 6 carbons, it's even more complicated. So again, in the Fisher projection convention, the highest oxidized carbon is always at the top. So we see that aldehyde is at oxidation state 2. The horizontal lines are projected towards you. The vertical lines, even if they're drawn in like a straight line or plane, they're always going back. And then the penultimate N-1 carbon bearing the hydroxyl group determines the D or L nomenclature. So which one of these Samuel Jackson is the naturally occurring Samuel Jackson? What's his middle name? You think it's D? Isn't it L? So I think it's Samuel L. Jackson, right? So this is the naturally occurring. And then his twin, his enantiomer, is Samuel D. Jackson. I don't think he has a twin, but basically these are mirror images of him. And if you've watched Star Wars, he was Mace Windu, the Jedi Knight, and apparently his favorite color is purple. So what was that other movie, like Unbroken or something? He was in another movie where he played like this guy that liked comic books. It had Bruce Willis in it. Glass, is that? Yeah. So apparently his favorite color is purple, and in that movie Glass, like most of his outfits were purple. So there's a little side note of movie history there. So again, when we start looking at the higher order carbohydrates, the Fisher projection is pretty important for us to determine relationships. And so if we follow the logic of going, I guess we'll redraw this. So H. I always draw the last alcohol to the right. It doesn't matter because that carbon is not a stereocenter. So I mean, if we drew it, with a bond rotation this way, that's still the same molecule. It says if we constrain all aldoses to having an aldehyde at the top and the primary alcohol at the bottom, the internal alcohols are all secondary. So this is internal. And again, the last one is the terminal. So that's always primary. So internal are always secondary. And from a chemistry perspective, that's important because you've sort of differentiated. You have one primary and then the rest are secondary. So that sort of speaks to selectively acting upon the primary before the secondary. And so if we're moving up now from 3 to 4 carbon chain, so I'm just going to draw the chain like that. The aldehyde is at the top, that's carbon 1. carbon 4 is the primary alcohol. So now we have 2 carbons in between, and we just draw them with horizontal lines. The question says, how many stereogenic centers will this have? And so the stereocenters are now carbons 2 and carbon 3. And so I'll put an asterisk by them. So we use that 2 to the n, so n is equal to 2. So now we get 4 stereoisomers. The specific answer to this question is 2 stereogenic centers. And I think the next question, the answer is 4, because it's 4 total stereoisomers. And so if you look at, these, what are we putting on the horizontal lines here? You're adding H and OH. And so there's 4 ways you can do that. So 2 to the 2, that gets us our 4 stereoisomers. And so when we think about stereoisomers, again, there's enantiomers that have opposite RS designations. And then there's diastereomers where one of those designations will change. At least one of them. So any questions so far? Basically what we're going to do for the rest of the lecture is now look at building up sort of the tree of these carbohydrates in their names. So again, we do not typically use the IUPAC names because they'd be like this long. They're given these common names. So the most common one is what sugar do we use most commonly? Glucose. So again, glucose has a structure, and then the IUPAC name is pretty long. We just call it glucose. So this slide is showing you aldotetroses, so the 4-carbon chain aldoses, and we said there were now 2 stereogenic centers, so 4 total stereoisomers. And of that, we have 2 pairs of enantiomers. And then every other relationship is diastereomeric. So if we focus on the center 2 structures, these molecules, again, there's the IUPAC name, but they're commonly called erythros. So notice here in the left structure there, that OH is to the right, so that's the D erythros. The negative sign is what's measured in the polarimeter. And the logic of going from 3 to 4 to 5 to 6 is you're sort of inserting carbons internally. So in this logic, at carbon 2, we put an OH group to the right. Then its enantiomer, both of those OH groups are to the left. But the L only, again, refers to the penultimate. So if we look now at the D erythros, if we keep the D configuration the same, but we swap out the H and OH at carbon 2, so now the OH is to the left here, that's called threose. So because that D configuration stays the same, it's still D, but the threose is telling you that at carbon 2, the stereocenter changed. The enantiomer of threose is shown all the way to the right, where you have the carbon 2 OH group to the right, the carbon 3 OH group to the left. And so when I refer to these, I'll typically say like right, right, or left, right, or how many other stereocenters there are. That's again referring to the OH bonded to that carbon. One other thing that's used, one other piece of nomenclature is this word epimer. Epimers are diastereomers that differ only at one specific carbon. So in this example, if we look at the two structures here to the left and then this center one, carbon 2, see how that stereocenter just moves? So we would say that that's a C2 epimer. So D3-ose is the C2 epimer of D-erythros. So the epimer just means one of those stereocenter configurations is changing. So moving on now, if the carbon backbone is then elongated by one carbon, so we go from 4 to 5, we're making pentoses. And so the question asks, how many total D and L aldopentoses are there? So this word, where is it? Progeny. So that just means children. So in the tree, as we move up the chain, each sugar is giving birth to 2 progeny. So now we have 3 total stereocenters. So 2 to the 3 gives us what, 8? So for the pentoses, there are 8 stereoisomers. If we take 8 and divide by 2, we get 4. And so that means there are 4 of the D configuration and then 4 of the L configuration. So 8 total, and then 4 plus 4 based on that penultimate configuration. So on this slide, I'm only showing you 4 stereoisomers of the D configuration. And what you have to imagine now is that each of these 4 has the mirror image enantiomers, and that's the L configuration. So what is the logic? As I said, since each one gives birth to 2, so D-erythros gives rise to D-ribose and D-arabinose. So maybe one way to think about this, if we look at erythros, see the bottom carbon, the last carbon is always a primary alcohol. So if you read it from the bottom to the top, these 2 carbons, see how they're both right? In ribose and arabinose, those 2 carbons are still right. Then the carbon that you've added now is sort of inserted between the aldehyde and the former carbon 2. And you're just swapping whether it goes right or left. So that's why it gives rise to 2 kids. And so ribose is right. And do you know Does ribose like ring a bell with any other sort of molecules that you might be familiar with? What do you think? RNA. So that's ribonucleic acid. So the ribose serves as like the sugar backbone for that. And then DNA is deoxyribonucleic acid. Deoxy means you've deleted one of those OH groups. And so when I talked about that abiotic sort of synthesis, abiotic just means you have everything that's like inert or dead evolves into something living. So I mean, we're living beings with thought, consciousness. But if you look at us down on the molecular structure, nothing in us is really alive. We're just a collection of atoms and bonds, right? So at some point, there's something that gives us thought and consciousness. And ribose is a key sugar in sort of those molecules as they've assembled. So again, you're just seeing the D sugars here. Erythrose gives rise to ribose and arabinose. And now if you look at threose, see how those carbons are left and right. You see that retained left, right, left, right. And then the carbon you inserted, it's either right or left in the two children, which are xylose and lixose. So if we go from 5 now to 6 carbons, these are hexoses. And so how many total stereoisomers will there be? So we have 6 carbons. Carbon 1 is an aldehyde. Carbon 6 is a primary alcohol. So C2 to C5, 2, 3, 4, and 5, that's 4 carbon atoms. That are secondary alcohols that are all stereogenic centers. So now we have 2 to the 4, and that's going to get us 16 total stereoisomers. So we have 8D plus the mirror image is 8L. That gets us our 16. And so again, on these slides, I'm only showing you the D ones. So ribose gives birth to allose and altrose. So notice that the C2 goes from the right to the left. That's how they differ. Arabinose goes to glucose and mannose. So glucose is the most common sugar we're familiar with. And you can then ask the question is why is nature or whoever selected glucose? There's a specific reason why glucose is used in it as an energy source, and we'll talk about that a little bit later today. But just to put that other term in, the relationship between glucose and mannose, they are C2 epimers. So overall, if you look at them, they're diastereomers because you're changing one of those carbons. And specifically with carbohydrates, we say they're epimers. So xylose forms gulose and idose. Lixose forms galactose and talose. So I always think of these as like elvish names in Lord of the Rings or something. They're just very odd names in my opinion. But if you look at any of these and you pick two of them out, their relationships are all diastereomers. The enantiomers would be the mirror images. So the way that I remember glucose is you have 4 stereocenters, so right, left, right, right. That's along the Fisher projection if you had to fill in the OH groups. So glucose is right, left, right, right. And, you know, as you move on in your studies, you probably just want to make sure you remember that one. And then, you know, using these other terms like epimer, you can sort of figure out, you know, if you say mannose is the C2 epimer of glucose, that's left, left, right, right. So here's the tree of children, starting from the 4 to the 5 to the 6, how they sort of give birth to the next longest chain. And again, ribose is important for RNA, DNA. Glucose is important as an energy source. And then again, if you can imagine sort of a separate screen would project the L ones, which are all mirror images of those. So the next like run of questions, the logic behind this is, you have a question?
Yes. Do we need to memorize all of this, all the names?
You know, because the exams are online and open note, open book, I mean, you don't really have to memorize anything. It's good that you have an understanding of the logic so you can access like the facts quicker and understand the intent of the questions. But even if these were in-person exams, I wouldn't have you memorize this stuff because there's really no point in memorizing it because you could just look at the structure. It's more important to understand sort of the reactivity. So the next run of questions here is the setting or the context is, you know, at some point in human history, even though you're seeing these structures and they're proven for what they are, humans did not know what the exact configurations were. And Fisher, you know, we all know who Isaac Newton is, Albert Einstein. Fisher is like right up there in terms of his impact on science in human evolution, because he was the first person in human history to figure out the structure of glucose. And this was at a time when there was no IR, there was no NMR. You know, it was basically, you could take a melting point, you know what I mean? Or you could do some degradations and combustion analysis and stuff. But his intellect and genius, you know, you could say he made good guesses or the right guesses, but I think through logic, he figured out what the structure of glucose was using the questions that we're going to ask here. So again, if there were 16 total stereoisomers of the hexoses, he figured out the right one. And, you know, using his knowledge of chemical reactions, he was right. So this question is asking you, if you take sodium borohydride, which was a reducing agent we learned, and remember that only acted upon oxidation state 2 functional groups, so aldehydes or ketones. So an aldehyde reduced with sodium borohydride becomes a primary alcohol. a ketone becomes a secondary alcohol. So since we only have aldehydes in here at carbon 1, that carbon 1 is going to be the primary alcohol. And the question says, of these 4, when you run that, which one becomes meso? And do you remember what the word meso means? What do you think? Yeah, so a meso compound, it has to have stereogenic centers, but then what makes it meso is an internal mirror plane. So the molecule in it, you have to bisect it somehow, and like the top half has to mirror the bottom half. And so when you do that, which one of these becomes a mirror, has the mirror plane to form a meso compound? What'd you say? Yeah, it's going to be allose. So what is that structure? So again, carbon 1 becomes a primary alcohol. Carbon 6 is already primary. And then the sodium borohydride does not do anything else to those internal alcohols. So that would be the structure. And then what I'll draw in blue is where the mirror plane is. So we have 6 total carbons. So the mirror plane is going to be between carbons 3 and 4. So these two mirror each other, those two mirror each other, and then the terminal ones mirror each other. So that's the mirror plane. The stereogenic centers are 2, 3, 4, and 5. So it satisfies that word meso. So allose is the correct answer for this one. So that was a set of 4 of the 8 D isomers. This is the other 4 D isomers, and it's the same question. Which one of these is going to form a meso compound? Huh? Galactose. So if carbon 1's reduced, now the mirror plane will be right here. So those two mirror each other, these two mirror each other, and then 1 and 6 mirror each other. So again, the meso is referring to that internal mirror plane. The reason idose is not correct is, see at carbon 3 and 4, they're on opposite, so they don't mirror each other. You're crossing through that bond. So here's all of the 8 D sugars. The question is still using sodium borohydride to do a reduction. And it's saying when you reduce 2 of them, they will converge onto the same structure. What do you think? So maybe to help you out, a hint is that the symmetry element here is not a mirror plane, but an axis of rotation. So I'll show you the answer, and then we'll sort of draw some things out. So B is going to be the correct response. Altros and talose both converge into the same compound. So when you reduce altros, it becomes this. When you reduce talose, it becomes this. So those are actually the same compound. And can you see the reason why? So if I, in the blue pen here, I'm going to draw a dot. Where do I want to draw the dot? I think right here. So in that dot, if you put an axis and then rotate it 180 degrees, you'll see that the OHs on the right from the altros product become the OHs on the left in the talose product. So in sort of the common symmetry elements that we've seen so far, there's the mirror plane. This is, the second one here is called an axis of rotation, and then the third common one is called inversion. That's where you have like a center point where you can drag one functional group from one side to the other and you invert it. That one maybe is a little bit harder to spot, probably. So those two converge upon the same compound. So here's a separate question related to the axis of symmetry. So which pair, when you reduce them, they don't converge onto the same molecule, but they produce products that, when you find that point and rotate it, they have a 180-degree axis of symmetry. What you're looking for is what you start with, what you end up with. When you invert it, you're sort of getting the same molecule. Any guesses? Huh? So mannose and idose will be the response for this. So let's do mannose. If we reduce carbon 1 to the primary alcohol, the rotation axis will be right here where that blue dot is. So the two alcohols on the left, when you rotate it 180 degrees, become the two alcohols on the right. And so similarly, those last two alcohols on the right, you rotate, they become the top two on the left. So idose, you can see, is the same way. So maybe I'll draw this a little bit different way with these green arrows. So when you rotate those, they sort of take the same position. And then when you rotate these, they'll take those same positions. So let me cross this out. So we basically use symmetry to figure out that allose and galactose form meso compounds with the internal mirror plane. Altose and talose converge upon the same compound, so identity. Mannose and idose form C2 symmetry. They have a rotational axis. C is used in sort of symmetry elements. The 2 basically means if you take 360, divide it by the rotational axis, which is 180, that's how you get 2. So if you have like a molecule with other functional groups, you can have more symmetry. You can think things can be like C3, where now the axis of rotation is 120 degrees rather than 180. If you're interested in that sort of thing, you can take inorganic chemistry, where Dr. Wallace teaches you how to analyze symmetry elements more in depth. And really what you're doing is you're just following a flow chart with questions. Does the molecule do this? Does it have this? And you'll get to the right answer. So any questions as we slide into the last 15 minutes here? So a little bit more about the Fisher projection and what the reality really is. Again, the reason it was drawn was in the way it was to help Fisher understand, what things were enantiomers, what were diastereomers, what were epimers, in his quest to figure out what the structure of glucose was. So really it's to help you, as I'm drawing here in red dot, it's to help you figure out stereocenters. So again, that blue vertical backbone, even though we're sort of drawing that as in one plane, those vertical bonds are actually projected back at each point. And so if you make a model of this, it's not a line. It actually ends up looking almost like a ring. So as you go around, that carbon backbone actually folds back in on itself. So to highlight carbon 6 actually sits behind carbon 1 if you actually build a model of this. So the projection as a learning tool is useful for one thing, but the reality of it is quite different. And this sort of drawing has another name. It's called a Hayworth projection. And that's how that form, those two structures on the right, is typically how your biochem books or your biology books will draw carbohydrates. I guess the other thing I want to point out, remember how I said glucose was right, left, right, right? So really what you're doing in the Hayworth projection is you're looking at the molecule from a different perspective. And the convention is if you take that chain and sort of rotate it clockwise, what that's going to help you do is see that C2 alcohol, how it's to the right. Now here it's down. C3 is to the left, it's up. 4 and 5 are to the right, so they're down. And really where this is ultimately going, the Fisher projection helps you with the right, left, right, right. Hayworth is telling you, is it up or down? And then as organic chemists, ultimately, when this thing forms a ring, it's 6-membered, so we want to know, are those things equatorial or axial? And just to give you the short answer here, the reason that glucose has been chosen through nature is that when it's in a ring, all the substituents are equatorial. And we remember from Organic 1 that equatorial substituents are lower in energy than axial ones. And so nature has chosen that path for glucose. And so this slide shows you how that Hayworth projection actually forms the ring. So here's glucose in the middle in the, I'm going to say, acyclic form. We know that carbon number 1 is at oxidation state 2. So if you pay attention to this alcohol here, that's the carbon 5 alcohol. That can attack from the top or the bottom face of that aldehyde. And so when that forms a ring, it's a 6-membered ring, and the OH, which I'll color in green here, of that carbonyl, that OH can either go up or down. And so now here's another layer of hell to the nomenclature. The relationship between the leftmost and the rightmost structure, these are called anomers. And an anomer is a specific type of epimer. And so what makes it an anomer? That carbon number 1 now, it's still at oxidation state 2, but now it's sp3 hybridized. So the beta anomer has the OH group up. So OH group is up on carbon 1. The alpha anomer, OH group is down. So even in just glucose itself, the relationship between alpha and beta anomers, those are diastereomers. And so that configuration at C1, whether it's up or down, drastically changes the polysaccharides that can form. And I think maybe it's this lecture or next lecture, when you start linking them together, they form different substances with different properties. So the two anomers, the alpha and the beta, are shown in the center here. So remember, OH is down for the alpha, up for the beta at C1. They're diastereomers, and when you convert that Haworth projection into a chair, you can see that all the substituents end up equatorial. And that's keeping in mind that the anomeric carbon, one of them for the beta, it will be equatorial. For the alpha, that OH group is axial. But every other substituent on there is equatorial. So glucose, it exists in these three forms: the acyclic form, and then these two cyclic forms, the beta and the alpha cyclic forms. So if you take a mixture of glucose, you put it into water, you have all these OH groups that makes it soluble in water. It's going to form these three different structures in different percentages. And so the beta isomer is present in 64%. Again, that's the one with the most equatorial substituents, so it's sort of the most stable. The acyclic one is just trace because that OH group wants to cyclize to form the ring. And then the alpha one is 36%. Notice that the alpha and the beta, they're diastereomers, so their melting points are different. 146 is different from 150. And the other important thing to notice is, even though I'm still using that alpha there in the square brackets, that refers to specific rotation. And you see those values are pretty different. So the alpha is 112, the beta is 18.7. So a mixture of all of those together will converge upon this number here, plus 52.7. Which means, so for example, if you took the pure alpha anomer and you initially measured it, it would be 112. But over time, this equilibrium would happen and you would end up at 52.7. Alternatively, if you started with the pure beta at plus 18, it would still converge to 52.7 due to the equilibrium. So let me just see something real quick. The actual polysaccharides we won't see until Monday. So we'll probably just end on this slide that's showing you how the acyclic goes to the different cyclic ones. The rest of these slides are reactions that we can cover pretty quick on Monday. But it's saying what face of the aldehyde does that oxygen from C5 attack? And so a little bit of nomenclature. I don't want to do that. Let me erase that. So we know that to be a stereogenic center, the carbon has to have 4 different things. If you see in these generic drawings of these aldehydes, that carbon is sp2 hybridized. So it's not chiral. But when something attacks it, it will become chiral. And so we say it is prochiral. And so what I've shown you here is the 2 different faces of the aldehyde. And so we use these terms Re and Psi to determine which face we're looking at. And it's sort of determined in the same way as R or S. So of the carbon of interest, the sp2 hybridized carbon, you have 3 substituents, H, O, and then we'll just call R as carbon. And then we assign priority. So oxygen is the highest atomic number, so that's 1. Carbon's the next, so that's 2, and hydrogen's the lowest. So if we connect those, we see we're going counterclockwise. So the face that we're looking at from this perspective is called psi, Si. If we do the same analysis, 1, 2, 3, now we're going clockwise, so that's Re, Re. So if we wanted to form the alpha anomer, the left structure, it's asking you this green oxygen I'm highlighting, what face of that C1 carbon is it attacking? So let's put in our priorities here. 1, 2, and 3. And we see that we want the H group to go up, then this blue oxygen to go down. So what is that attacking? I'm gonna like move my brain around mentally to figure this out. What do you think it is? I think it's counterclockwise, so it has to be the psi face. What's tough about it, you almost have to put your eyeball like down here, like behind the screen, and then look up, because this OH is attacking from the bottom face, so that hydrogen ends up on top. And so if you're able to sort of visualize that, then you do the counting. I think it becomes counterclockwise. So we'll finish up on that today. And then on Monday, we'll look at some structure, some reactions, structures of polysaccharides, and then we'll look at sweeteners. So you'll taste natural things, then you'll taste like sweeteners. Why are sweeteners important? And then, you know, I've done the thing for like 2 or 3 years now with the sweeteners, and most students do not like the taste of the natural or the sweeteners at all. But when they're in solution, I guess they're not as bad, but if you taste them pure, they're not pleasant. So that's something to look forward to. Actions. Okay, so the rest of these are